think we'll get started and let people make their way in. So it's my great pleasure this afternoon to introduce Dr. Kristy to the University of Calgary and to give a presentation to a very diverse audience here. And I want to thank Walter for the time to be able to do this seminar in this time slot. And we knew we would have a good turnout, so it worked out very well. So thank you very much for that. Kristy is the co-scientific director and the director of engineering for the Center of Injury Research and Prevention at the Children's Hospital of Philadelphia Research Institute. And the short form for that is the CHOP Research Institute, as opposed to SHRED. Yeah. So she's a research professor of pediatrics at the University of Pennsylvania. And that is where she did her PhD and completed that in 1997 in bioengineering with a focus on brain injury. She's internationally recognized as an expert on pediatric injury and specifically brain injury biomechanics, injury causation, and the effectiveness of safety products as well as safety equipment for children and adolescents related to motor vehicle collisions as well as sport safety. She has a focus more recently on the use of head impact sensors to understand the biomechanics of sport-related concussion with the goal of improvements in protective equipment to enhance protection of young athletes. Her funding is diverse and she's had a lot of funding over many years from National Institutes of Health, Centers for Disease Control and Prevention, the National Science Foundation, National Highway Traffic Safety Administration, National Football League, as well as industry funding. So welcome and thank you very much for speaking up this afternoon.
Well, I'm really thrilled to be here. Can you all hear me in the back? Great. I've been here for a day and a half now and really had the pleasure of meeting such a diverse, multidisciplinary group focused on biomechanics and injury prevention here at University of Calgary. And so I'm thrilled to be given this opportunity to share a little bit of the work that I've done over 2 decades at CHOP and to identify hopefully some areas for collaboration. The title I have up here is actually a little different from the title on the pieces of paper I've seen plastered all around here, which is weird seeing your picture, because in addition to focusing on sports concussion, which obviously is an area of focus here at Calgary, I wanted to honor my road traffic injury roots and share with you some of the biomechanics work that I've done in that space as well. So I would say that this is one of my favorite quotes that kind of drives the work that we do at CHOP and the work that I do personally. It's from a former CHOP individual and former US Surgeon General. And the point that he was trying to make is that if unintentional injuries were viewed as a disease, we as a community would be outraged. There'd be a tremendous amount of funding directed to solving this disease. But the idea that unintentional injuries are accidents and when we think of pediatric unintentional injuries, that they're just part of childhood, kind of gets in the way of addressing this public health problem for children. And it's really this mindset that drives our work at the Center for Injury Research and Prevention at CHOP. So our mission is dedicated to advancing the safety of children, youth, and young adults through research and action. And there's 2 parts of that mission that I want to highlight. First of all, that it includes children, youth, and young adults. So our definition of pediatrics, pretty broad. And then the last word in that mission, which is action. And we, from the beginning, have taken an approach that we want to create impact. It's not just to study unintentional injuries from an academic ivory tower perspective, but to work with those at a grassroots level who are in a position to make impact on children's lives. And this may include industry, government, policymakers, advocates, You know, I'm not designing cars in my office at Children's Hospital, but I want to work with those that are, because our research is going to drive future designs. So we've looked very comprehensively at the injury problem, both prevention as well as accelerating healing and recovery. We're very interdisciplinary, and it's one of the things that I've really enjoyed over the past 2 days, learning that you too are very interdisciplinary. And we've been engaged, as I said, with many a diverse set of end users, because we realize that to impact injury prevention for children, we need to work with a diverse set of stakeholders. And then very translational, giving practical tools and recommendations to both professional as well as community folks that are involved. A little bit of context of my institution. So I work at Children's Hospital of Philadelphia. We have an ongoing fight with Boston Children's Hospital as to who's the top rated children's hospital in the US, and we're often flip-flopping back and forth. We were the first in the 1850s, and we're a level 1 trauma center in our state and a leading pediatric research institute. The relationship between CHOP and University of Pennsylvania is somewhat of a blurry one. They're financially separate, but many of us researchers at CHOP are faculty at University of Pennsylvania. And the fact that we are kind of geographically co-located really opens up a lot of opportunities for collaboration outside of the School of Medicine. We have all the schools, School of Law, School of Public Health, School of Communications, School of Engineering, that are all located on the same campus. So back to our injury center, we've taken this approach of research to action to impact, and that really guides many, and if not all, of the projects that we work on. It's anchored in epidemiological surveillance. We need to understand that the problems we're solving are real. And then using a variety of discipline-specific approaches, we dive deep in understanding those issues, doing in-depth study, whether that's engineering, whether that's psychology, whether that's more epidemiological and biostatistics analyses. We publish, we're an academic institution, we do that, we have to, but it's the intervention and the reaching out through these stakeholders to ensure that our results are translatable. And then we hope with our surveillance systems to be in a position to be able to measure the impact of that work. The areas of research that our center focuses on is fairly diverse. They're listed here on the slide and really encompass the diversity of disciplines of my colleagues at the Injury Center. The two areas that I have spent my career working in is pediatric biomechanics and concussion, and those are the two I'm going to highlight some of my work from today. We'll start with pediatric biomechanics. And that has been studied in the construct of road traffic injuries. And so why are we interested in road traffic injuries? Well, as a children's hospital, we're interested in the leading cause of death for kids. So globally, road traffic injuries ranks among the top 4 leading causes of death for children greater than 5 years of age. I'm proud to say that when I started this career, we used to say that for ages 1 and up, and by many researchers, we've made strides on our youngest kids, but we still have an important task at hand for those that are age 5 and up. And then if we think of our teenagers, it's the leading cause of death globally. Every year, close to 200,000 children less than 18 years of age die on our roads. If I share with you some US data, which I think is fairly exemplar of many of the developing countries, we've had reductions. If I would plot this graph, this is annual motor vehicle fatalities less than age 14 in the US. If I would plot this graph back 10 years, you would see that the number of fatalities hovered around 2,000. So we made strides in reducing that to about half. But you can see for the last maybe 5 to 7 years, it's been pretty flat. So advances made, still the leading cause of death. So from a pediatric hospital's perspective, it's still something that we want to focus on. And this idea has been embraced globally by the road traffic safety community with this concept of Vision Zero. So Vision Zero was originally introduced by the Swedes. They're usually at the head of road traffic safety initiatives, but it's been embraced by virtually every developing country, including Canada and various cities in the US, of the idea that we should have 0 fatalities, literally 0, and 0 serious injuries on our roads. And so there are lots of initiatives, both research, education, and policy, that are occurring in these countries to try to reach this Vision Zero objective. Our viewpoint of the contribution that we could make to that Vision Zero perspective from a biomechanics standpoint was focused on collecting fundamental data that would help to improve the tools that the auto industry had to use to design motor vehicles, restraints, airbags, seatbelts, car seats. So when we started this work back in the mid-1990s, the pediatric crash test dummies were simply size scaled from adults. They recognized the size differences, which were somewhat obvious, but did not have the fundamental data, the fundamental biomechanics data to implement in this tool what we could observe anecdotally, that kids had different biomechanical characteristics. Their tissues were different, they had different joint properties, their relative body segment lengths were different, and all of these things are going to influence their kinematics in a motor vehicle crash, but the tool that the auto industry was using to advance safety for kids simply did not reflect how real kids might respond in that crash environment. So we went after this problem with the idea of developing, of collecting the data that would lead to the development of an ideal tool. So this tool needed to kind of look and feel like a kid, needed to be the right size. They had kind of gotten that part right. But more importantly, it needed to move like a human child and have the overall motion and kinematics that real children have, and then predict human-like injury, predict the right injuries. So kids sustain different injuries than adults do. And so we needed this tool to be able to predict the pediatric specific injuries. And it needed to include diverse injury types, not just skeletal injuries, but also soft tissue injuries, particularly for kids where their skeletal system may be in a position to withstand more load. And it's the soft tissue injuries that we may be more concerned about. So we set about a biomechanics program to try to fill in these gaps and to provide the auto industry and those that make the pediatric crash test dummies with the fundamental data to create a better tool. And so if we looked into the early 2000s, on the left, there is a video of old work that was done in Heidelberg, Germany, using a pediatric cadaver. That work is very rare, far and few between, where we have that quality data to understand how a real human moves in response to a crash loading environment. On the right, we had the current state of the art of pediatric crash test dummies. And so what I want to draw your attention to is the spine and the spinal kinematics. What we see in the human on the left is that C shape, that the multi-segmented spine results in flexibility that allows them to wrap around that seatbelt. In contrast, what we see in the crash test dummy, because they have a rigid spine, all of that flexion occurs at the upper neck. And so we get an inaccurate representation of neck loads. We also get an inaccurate representation of head excursion. And if we look at motor vehicle crash data, head injuries are the most common injuries sustained by children, regardless of what crash direction, what age, what restraint they're in. So we knew having this tool, being able to accurately predict where the head went, was really important. And we saw, based on these comparisons, that we probably weren't doing that really well. So we knew that given kind of current ethical standards and this kind of state of knowledge of the field, that doing a large-scale pediatric cadaver study was not going to be viable. Funding agencies weren't really interested in biting that off, and different industry sponsors weren't interested in doing pediatric cadaver work. So we had to think about an innovative way to collect this data in a way that would give us a hint of what the kinematics should be without kind of going down the pediatric cadaver route. So we thought about how opportunities where kids are loaded in a dynamic way that is safe, that kids participate in voluntarily, and we immediately turned to the amusement park industry. So kids do all kinds of things at amusement parks that are very dynamic. For the most part, they're safe, and they emerge injury-free. So we had a very fun field trip to one of the amusement parks near Philadelphia. We instrumented via an accelerometer a bunch of the amusement park rides and ended up focusing on the bumper car. So everyone knows what a bumper car is. You get in the car, you run into other bumper cars. And the response of the participant, the amusement park rider, is very similar to what you might experience in an automotive event, albeit a lower severity. So what we did is we took that crash pulse of a bumper car, came back to the laboratory, and created a low-speed human volunteer sled that could mimic that loading environment, so we knew it was safe, but also give us some insight into the dynamic kinematics across the age range. So we had here we go, there we go, a idealized seat that sat on this cart. It was pneumatically driven backwards, hydraulically controlled via brakes, and we studied children as young as 6. Would have loved to go younger, but I couldn't deal with 3 and 4-year-olds following instructions. Kids as young as 6, up through adults, using motion capture, we were able to study the head excursion and the spinal kinematics and put quantitative values to what we knew through observation that kids move differently. So I'll show you this. See if I can. There we go. So this is one of our 12-year-olds. You see the motion capture markers, high-speed video of a low-speed event. The crash pulse was about 5 miles per hour. The maximum acceleration was about 4 Gs. And so we were able to characterize the kinematics. We were particularly interested in the spine, the torso, and the head. And we made observations of fundamental differences in how kids move and how people move across age. So we saw that the 6-year-old moved farther forward relatively and further downward. And so if we summarize that, we saw that this is kind of looking sagittally at the head movement. The fore-aft movement is on the x-axis. The vertical movement is on the y-axis. That as you got older and taller, your head path became shorter and it became flatter, less loopy. And you can imagine that if we designed a pediatric crash test dummy based on our adult data up here, and we just made it smaller, it's going to have a different excursion pathway in a crash than if this is really how a child moves. And so this data helped us understand how we needed to change the pediatric crash test dummies to be able to mimic real children. And when we looked at it in more detail, it came down to this thoracic spine flexibility. So this shows the points of the various motion capture markers for an average 6-year-old, average 30-year-old at the beginning of the event, and then at the end of the event. And you can see that that C shape that we saw in that cadaver test was able to be replicated in this lower severity event. And so this data has led to an improvement in crash test dummies. There is a new dummy being evaluated by the US Department of Transportation that incorporates this data and has a more flexible spine. And so we're hoping, the US DOT moves rather slowly, but we're hoping that this will lead to a better tool that the auto industry has to better design restraints for kids. The next area of biomechanics that we are currently focused on is the idea of pre-crash maneuvers. So it is likely rare that you are in a crash and you drive right into whatever you're running into. There is probably some avoidance maneuver that you are doing, braking, swerving, to avoid the crash. That avoidance maneuver is going to displace you as an occupant. It's going to change your occupant state. And probably most importantly, it's going to move you away from that optimal position that the restraint was designed to function in. You know, if you're swerving and you're moving out, if this is the belt and you're swerving and now the belt is here and this is when you crash, well, that's probably not how we hoped the restraint was going to work. And so what we've focused on most recently is, can we characterize, again, across the age range, this kinematic response to pre-crash maneuvers. So we have another device that provides an oscillatory swerving. I have a video on the next slide. So it's a regular vehicle seat in this kind of cage that is surrounded by motion capture cameras. We're measuring the reaction forces of the seat belt, the seat itself. They have a little footrest that they put their feet on. And we are interested in characterizing kinematics through oscillatory swerving to mimic that emergency avoidance maneuver that might precede a crash. So we do 4 cycles of oscillation. 1 cycle of oscillation moves that cart about 2 meters down the rails and back. And the subject initially moves away from the belt. So here we have one of our adult subjects. So they initially move outside the belt, into the belt. And we're interested both in characterizing the kinematics relative to the belt. So what is the torso doing? And then we are using wireless EMG to understand the muscle response and the role of bracing to control that movement. There is some evidence to say that children, in this study we're going as young as 9, have less neuromuscular control to be able to respond in a way to help use their muscles to control that. We're evaluating a variety of different countermeasures, advanced designs of the seatbelt. We're looking at sculpted shape of the seat to see if those vehicle-based countermeasures can help control that motion. We're just finishing data collection, so I don't have the whole story for you here today, but just to give you a sense of what kind of data we're collecting, this is looking at the lateral displacement of the suprasternal notch, looking at the baseline restraint condition, and then an advanced restraint condition that kind of pulls the slack out of the seatbelt right before the event happening. And so you can see that the motion is reduced by about 1/3 if you apply that countermeasure. So the approach that we're taking here is to try to understand how real kids move, how that varies across the age range, and then what technical countermeasures might we implement to control that. The last area that we've been focusing on in traffic safety is this intersection between behavior and engineering. So back to my auto industry colleagues, they design based on this. They have the crash test dummy, which I've already shown you may not be the best tool, but they position that dummy upright, back against the seat, sitting perfectly. many of you that have children know that that's not what they do. They do this. They move, they're leaning, they're talking to their sibling. And it is my hypothesis that when we look at the crash data and see that restrained children are still getting injured, I think it's at this intersection of behavior and engineering that we're failing, that we haven't designed a restraint system to protect this guy who's playing with his iPhone. We've designed the restraint system to protect him. And so through a collaboration with Monash University in Melbourne, Australia, Jude Charlton was the PI there, we implemented a naturalistic study where a study vehicle was implemented with 8 cameras, and most importantly, a Microsoft Kinect system to give us a sense of where people were positioning themselves as they kind of went about their normal driving business. A participant family would have the instrumented vehicle for 2 weeks and just use it in their normal driving. The videos were used to give context to the scenarios, but we used the Microsoft Kinect system to be able, again, focus on the head to understand how children position themselves. And so this work led to this kind of data. So let me orient you to what you're looking at. This is the range of head positions that children assumed in normal driving viewed from above. We have 3 different restraint types: a harness-based child restraint, booster seat, and seatbelt, because that was the age range of children we studied. This is children in the left rear seat, the center rear seat, and the right rear seat. And then the colors represent the frequency of head positions during normal driving. So yes, you have a normal position, and that probably isn't so unlike that dummy position that I showed in the previous slide. But then we have this range. We have a range of, we've studied this kind of red range as common, but different than the standard position. And then there's kind of these extremes in black. You can't pick when your crash happens. So if you're the child that's up here, leaning substantially forward, and that's the moment of the crash, it's not surprising that they're getting a head injury from contacting the seat in front of them, because they're about 10 centimeters forward from what that restraint system is tested for. So this information, again, has been fed to the auto industry to allow them to innovate. If they know that positions vary by this much, maybe there is technology in the seatbelt that senses that displacement and pulls them back. Maybe there's just a warning to mom and dad, hey, kid's out of position, say something. The intervention isn't clear yet, but until we collected this data, we didn't know what the problem was we were trying to solve. So I would say from a biomechanics standpoint, what our work has done is try to bridge the difference between these standardized crash test dummies and real kids. And we want to protect kids, not dummies. And to reach that vision zero and further reduce the numbers that we've seen, we believe that from an engineering perspective, this is where the advances need to happen. So I hope that's given you a little vision of our auto safety work before I transition to the concussion work. So back to our research priorities in concussion. You know that it's an important issue when there's a movie. That there's been, no one in this room can deny that there has been international attention to this issue. But I think also in the scholarly community, there's been a tremendous amount of attention. Just last week in preparation for this talk, I just went on PubMed and did a quick, search of concussion for 2017. There were over 1,000 articles published. The attention to this issue from a diverse set of disciplines is undeniable. Some of that is appropriately directed. Some of that is driven by the media frenzy around this topic. But we know that this is an issue that affects children. The idea that children have lingering effects and long-term consequences from concussion is real and impacts their athletic performance, impacts their academic performance, and impacts their quality of life. So again, from a pediatric healthcare institution, this is something that we want to understand further. I was fortunate to serve on the U.S. Institute of Medicine committee that focused on this issue, sports-related concussion in youth. We issued a report in 2013, and the goal of that effort was to really review the state of the art at that time and issue a series of recommendations, which honestly read like a research roadmap, because there are so many gaps in our understanding circa 2012, 2013 that laid the groundwork for what we as a scientific community needed to focus on. And so it's nice to see that many organizations, including the group here in Calgary, have begun to fill some of those gaps, but we still have a lot of unanswered questions. Those unanswered questions aren't being helped by the media. You can't listen to the news, open a newspaper or a sports-related magazine, and see these debates that are happening, some with misinformation, but the idea that sports may be risky for children and that we need to do something about it is heavily debated in the lay press. As a parent of two sport-playing teenagers and young adults, it's heavily debated on the sideline, and there is a urgent need for information about prevention, both primary prevention of the injury happening, and then more secondary and tertiary prevention of long-term consequences happening once the injury happens. And I think this isn't only driven by the lay press frenzy, it's also driven by data. So this is some of Don Comstock's data out of the high school RIO system, just showing as an example the increase over the last few years in concussion rate in both practices and games. So it's real, and there are many unanswered questions. And from my perspective, from an injury prevention perspective, for us to tackle this, we have to answer three questions. What is this clinical thing we're trying to prevent? And for that, we need objective, age-specific markers and metrics for diagnosis and recovery. Who's at risk? And then what is the mechanical event that leads to this injury? And you can see that those questions involve various disciplines. That first one is rooted in clinical medicine. We need our clinicians to tell us what they see on the front lines. The second question is rooted in epidemiology. We need to understand if that one kid that walks through our door is exemplar or he's some weird combination of something. And then the third question is where us engineers come in, is understanding the biomechanics. So I'll share a little bit about what we are doing at CHOP to help answer each of these three questions. So what is the clinical entity? I am really fortunate to work in a wonderful clinical network where I have a sports medicine team of sports medicine physicians, athletic trainers, nursing colleagues that have really sharp clinical insight. We're also a pretty large network, such that in fiscal year 16, we had 12,000 visits for concussion for 5,000 patients, and our sports medicine department alone had about half of those patients. So we are, I hate to say blessed, but we're blessed with seeing the diversity of how concussion presents. One of my closest sports medicine colleagues, Christina Master, often says that concussions are like snowflakes. that, you know, each kid presents very differently, their trajectory may be different, but if we look at things in large enough numbers, I think we can begin to define those phenotypes. So just giving you a sense of our network, the map you're looking at here is the lower right corner of Pennsylvania and New Jersey, for those of you that aren't US geography savvy. CHOP, our home office, is kind of located here, where we have a 500-bed hospital, an emergency department. But throughout the greater Philadelphia area, we have 14 specialty care sites, which is where our sports medicine clinics are located. And then we have 31 primary care pediatric practices that also see a large number of our concussions. And so it's a socioeconomically diverse and racially diverse population. So back in 2011, as part of a patient safety initiative is really what got us started. We recognized that children were presenting at all of those diverse locations and, you know, airing some CHOP dirty laundry, they were getting different care. If they came into the emergency department, they were getting one approach to clinical care. If they came to our sports medicine department, they probably were getting kind of the highest level of care. And then we had our pediatricians who really hadn't gotten much concussion training in their medical training, who were on the front lines. And so we were able to use some internal funding focused on patient safety to really try to standardize clinical care and facilitate network-wide research. We developed a clinical decision support tool that lived in our electronic health record. We did training with our primary care providers, created standardized patient-family education materials, and then created a website that was accessible throughout the network to provide consistent messages. And so one of the first things that we studied in using this network was where were people going for their concussion treatment. And so the research question we asked is, where did they start their concussion treatment? So where was their point of healthcare entry into the CHOP system? And so we found what we knew anecdotally, that about half our kids were starting in primary care. They were calling their pediatrician, that was who they had a relationship with, and that was where they were going for that first line of questioning. We looked a little further, and if you actually had a CHOP primary care pediatrician, you were even more likely to start there. And so we knew very clearly that we needed to empower our primary care network to be able to deal with that. They saw their role, but they felt inadequately trained. And this is really where this clinical decision support and primary care training came. And there is no reason to suggest that at least for that first week or two, that a primary care physician can't care for concussion. If they go on to develop longer term consequences, yes, they need to be referred to a specialist. But as that first 1 week or 2 week caregiver, a primary care physician can do that job. To focus on objective diagnostics, we have a relatively new grant that started about this time last year. It's a collaboration between myself, my sports medicine colleague, Tina Master, and then Susan Margulies, who was originally at Penn Bioengineering and now is at Georgia Tech. And our goal is really to address this subjective marker question. We wanted to identify validated, objective, multi-domain assessments for concussion diagnosis. And our aims are really threefold. First is to use bioengineering technologies that measure balance, ocular motor function, cerebral blood flow, visual and auditory processing as a suite of objective markers that we use in the clinic and compare that to kind of the traditional self-report symptom-based diagnoses. And so we're doing that within the CHOP sports medicine clinics. And then Susan's role to use her juvenile porcine model to study mechanism at a very detailed level, to relate impact magnitude, impact direction to symptoms, neuropathology, and blood biomarkers. And then the third aim involves a partnership with a local school in the suburbs of Philadelphia to use head impact sensors to quantify their biomechanical load during a given athletic season, and then pair that with our suite of objective markers pre and post season to understand how biomechanical load relates to maybe changes in those markers. So I don't have data to share with you from this, as it just started about 9 months ago, but we're hoping to be able to answer some of these important questions. So who's at risk? One of the things we've really tried to convey whenever we talk about this issue is that a lot of concussion research focuses on the kids here in the light blue, the 15 to 17-year-olds. There's a little work done in 12 to 14, but kids of all ages sustain concussion. And concussion looks very different in these kids that are 5 to 11, and goodness knows what is concussion in a 0 to 4-year-old. Really hard to diagnose, hard to kind of tease out. But the issue that concussion affects all, concussion is not a sports-related issue alone, is a message that we've been trying to convey with our data. We have a paper in review that I've been waiting to hear the acceptance any day now, hopefully, but it's gone through one revision, that has provided some numbers to this. So we looked at that population and identified what proportion of subjects experienced their concussion via sports and recreation. And overall, that's about 70%. So you could look at that the other way, that 30% experience it from other reasons. And you can see that there's definitely an age effect of that, which makes sense. Hopefully we don't have too many 0 to 4-year-olds in organized sports. We have some. But the role of sports and recreation plays an increasing role as kids get older. But how we view this data is this discussion in the US, at least, of banning contact sports, banning football, isn't going to take concussions away. Concussions come from life, and we can't ban kids from life. And so we want to add kind of facts to the conversation about this story of pediatric concussion. And so if we look at kind of the converse of that bar graph that I just showed you, so if it's not sports related, what is it? It's a variety thing. It's falls, and that's probably predominantly where our 0 to 4-year-olds are getting their injuries. Motor vehicle crashes, so I do get to relate to my earlier work. And then we joked that in this figure that lives in this paper that's being reviewed right now, we wanted to have a category of like stupid things kids do. That's how they get concussions. And we can't prevent them from doing that. Kids are going to do those things. And so understanding that prevention strategies as well as awareness of the injury needs to extend beyond the athletic field is a message that we're trying to convey. What are some other characteristics of at-risk kids? So an emergency medicine fellow, Dan Corwin, published some work in 2014 and 2015 that looked at a cohort of kids that presented to our concussion clinic, and about 80% with vestibular abnormality on clinical exam took a longer time to return to school, took a longer time to return to sport. We also looked at pre-existing comorbidities, anxiety and depression. And those that had those mental health diagnoses on board, diagnosed before the injury, we're not talking about these diagnoses developing after the injury, they had a longer period of time till they were symptom-free, or a greater proportion of them were symptomatic at 4 weeks. So we're beginning to tease apart what are some of those risk factors that would allow the clinician at the kind of point of acute presentation to be able to identify you're going to have a longer time course of recovery. Another area we've been focused on at CHOP is vision deficits. This was not something that our pediatricians were using. They did not look at kids' eyes or didn't look at them in the right way. These ocular motor deficits are really common post-concussion. Looking at a cohort of 100 kids, 11 to 17, who presented to our sports medicine clinic, about 70% had vision diagnoses, including accommodation disorders, convergence insufficiency, and saccadic dysfunction. And so looking for these things allow you to identify some of these deficits. And you can imagine that a child with these vision disorders, we send them back to school. They're trying to take notes. They're trying to look from the board down to their notepad, their computer, whatever. It's not surprising that they're experiencing challenges. And these deficits can be rehabilitated. Working with some optometrists in the Philadelphia area, we've been exploring the role of vision rehab to correct some of these deficits. And so lastly, I want to talk a little bit about the biomechanics of concussion and how we might be able to answer some of these questions. So I don't think I need to share in this audience, but just so we're all working from the same page, concussions occur both from linear movement as well as rotational movement. And understanding the components of that is important from a biomechanics standpoint, and it's likely that every impact that a child experiences on the athletic field in a motor vehicle crash that leads to concussion is some combination of both linear movement and rotational. And so the way we as engineers look at risk of injury is through injury risk curves. So on the x-axis, we have some engineering metric. We'll just generically call it head acceleration for now. And then on the y-axis is the risk of concussion. And the first point that I always raise when sharing this with non-engineers or kind of statisticians or epidemiologists is this isn't linear. So a similar reduction in our injury metric, or in our engineering metric, does not result in a similar reduction in the risk of injury. So if we look at my kind of idealized examples here, where we have the kind of same reduction in head acceleration, this reduction is going to have a meaningful reduction in our risk from 75 to 50%. But if we have that same magnitude of reduction and we're down here on the curve, we haven't really impacted risk at all. And so when I hear helmet manufacturers or kind of these various add-on devices that go with helmets say that they've reduced force, or they use various engineering terms, by 30%, I'm kind of like, well, where are you on this curve? If you're reducing by 30% and we're down here or we're up here, well, your device, whatever you're trying to sell me, isn't really going to impact concussion risk. And so the definition of these injury risk curves is a fundamental contribution to the literature that really needs to be done. There's kind of a philosophical question, is what level of risk is acceptable? Are we talking about injury prevention? Or are we talking about injury mitigation? And so again, going back to my auto safety world, so we have very well-defined injury risk curves. So this injury risk curve looks at chest acceleration and relates that to the risk of AIS-4 thoracic injury. And what I've shown here is how in the US we rate cars by stars, one star car, 5-star cars at best. So a 1-star vehicle, there we go, has a 45% risk of thoracic injury. A 2-star car has a 35% risk of thoracic injury. But even a 5-star car, so this is the best ranking, comes with a 10% risk. So I think we as a concussion community need to think about what level of risk is acceptable. And maybe that risk is different if I'm talking about a 5-year-old playing sport versus a varsity athlete versus a professional elite athlete. But it's kind of a philosophical question that I think we need to wrestle with. Do these injury risk curves vary by age? Absolutely. This just shows an exemplar schematic of the time course of brain development, cerebral blood flow, synaptic formation, and we see that that extends well into young adulthood. So it's not surprising that an injury sustained by, let's say our little 5-year-old here, might have a different effect than the injury sustained by our 17-year-old. So when you hear about an injury risk curve for concussion, we need to have that be age specific. Does it vary by sex? Maybe. I don't think we know. What we do know is that, again, using Don Comstock's data, if we look at equivalent sports for girls and boys, we see that girls have a higher rate of injury. Is that biomechanics? Is that physiology, hormones, endocrine? Is it girls report symptoms more and are less likely to suppress disclosure? We don't know, but there is potentially a biomechanical effect here. If we think of girls have slenderer necks, less muscular development, and so the biomechanics of that and how that would feed into an injury risk curve likely varies by sex. Does it vary by the number of concussions and the interval between those concussions? We think so. Don't really know, but in the concept of repetitive injury, if we think about other body regions, we know that thresholds go down if you have sustained that injury once. And so this probably impacts the injury risk curve for concussion. We know it varies by direction of head impact. Some of the seminal work from University of Pennsylvania shows the importance of impact, importance of direction, excuse me. And so the idea that these injury risk curves are going to drive our prevention efforts, we have a lot of work to do to be able to define these injury risk curves. Two methodologic approaches that have been used is one is using large animal models where you can carefully describe the engineering input so you can really well define the x-axis. You can't really define the y-axis as well. We have scaling challenges, and then not all human clinical outcomes can be adequately represented in animals. Many of them can, and large animal models have a role here, but it's not a perfect match. So the other way people have chosen to define real-world injury events, injury risk curves, is to study real-world injury events. So this is, real human physiology and biomechanics. And we can systematically assess the clinical outcomes, but we can't control the engineering input. We can't control magnitude and direction of loading. And so then I want to end by talking a little bit about the role of technology to define the x-axis in these injury risk curves if we are studying real-world events. So what do we measure? What is the metric we want to use? How do we do that? There is a proliferation of ways to do this via commercial products. They have accelerometers in helmets, on patches, in headbands. And the idea of having accurate and reliable measures from these technologies hasn't necessarily been adequately discussed in the literature. So I had a graduate student, Mari Allison, who kind of tackled this topic as part of her PhD work. At the time, she looked at 2 helmet-based head impact sensors. She looked at the head system, which at that time was the most used in research. That system uses single-axis linear accelerometers that are embedded in the padding of the helmet. They are spring-loaded to improve head contact, and then they have an algorithm to estimate rotational acceleration from the arrangement of linear accelerometers. Another system developed here in Canada, G-Force Tracker, included a triax accelerometer and gyroscope, so they were directly measuring the rotational loading
but their sensor went on the outside of the helmet. And so there was question as to, well, what is it measuring? Is it measuring helmet motion, or does it have a relationship to head motion? So what we did is we took a rigidly mounted adult male crash test dummy head and neck. We used the hockey examples of these head impact sensors. We weren't necessarily picking on hockey. It was just something we could get our hands on. And so we used a pneumatic linear impactor, put the helmet on the crash test dummy as best we could using USA hockey guidelines. We varied speed, we varied direction, and we were particularly interested in varying the head helmet's surface. So for those of you that haven't held a crash test dummy, it's a big rubber surface, which probably very inadequately represents the biofidelity of how a helmet interacts with a real head. So we put a human hair wig on our dummy, and then we wet that wig to simulate perspiration. Hockey players are sweaty. And so the questions we wanted to answer is, and in the crash test dummy, in the CG of the crash test dummy head, there is an accelerometer that accurately measures what's going on. So that was our truth. So is the relationship between these sensors and the reference measure like a one-to-one relationship? So is 50 Gs from the sensor equal 50 Gs true? Does that relationship vary by these impact directions and other usage characteristics? And then what are these errors? So at the mistake of reducing her entire dissertation to one slide, she always gets angry with me about, this is kind of the headline. So let me walk you through these 4 graphs. On the x-axis of these graphs are the head impact sensor. On the y-axis is our truth, our dummy measure. The ones on the top are the hit system. The ones on the bottom are G-force tracker. And so there's a few things to take away. First, there is a relationship. So yay, these sensors do predict what the head is experiencing. If we go back to our questions, do they predict kind of a one-to-one relationship? The answer is no. If we look at, for example, we'll pick on the hit system here. So 80 Gs measured in the hit system, and it is about maybe 100 to 120 in truth. Worse in rotation, so 6,000 in the hit system is probably like 11,000 in truth. And then the other thing to take away is the variability. So here we have met across our different usage characteristics about 11,000 radians per second squared in truth. And we get a range from like 5,000 to maybe 8,500. So what we were able to do with this data is characterize the error. And I think any engineer understands the issue of error. Sensors have error, and you can incorporate that analytically. So we looked at kind of the raw data. Take the system value minus the truth, divide by the truth, and multiply by 100, standard way of calculating error. Then we tried to fit a relationship between the data and adjust our system measures. And so here's what we have. Here's the raw error, linear acceleration, angular. We looked at 2 different hockey helmets to see if it mattered. For the G-force tracker, for the hit system, raw, in the black headings, adjusted via the power of fit in the red headings. So you can see that the raw values aren't so great. 100% error isn't going to give you a whole lot of confidence. You can make that better. You can adjust that and calculate, account for that. And so this information was really the first time people began to question whether these head impact sensors were accurate, and could we include this error analysis in the creation of injury risk curves. So what does this mean for head impact sensors? I really like this paper out of the UNC group, Jason Mihalik and Kevin Guskowitz. they looked at measures from head impact sensors from players, of UMC football players. So they knew what the sensor value was. They knew whether they were diagnosed with a concussion or not. They calculated for a variety of different thresholds the sensitivity, specificity, positive predictive value, and negative predictive value. So the parameter you care about really is the positive predictive value. And they found that regardless of what threshold they set, all of these had extremely low positive predictive value, such that you would be screening way too many people that had a high sensor measure for injury, and you'd be sending most of them back on the field. Now, maybe for kids, that's appropriate. If we're talking about 5-year-olds playing Pee Wee football, well, maybe that's a good thing. At a Division I college level, that's not going to fly. We can't be pulling all these guys, these uninjured guys, off the field because their sensor value was high. So I thought this was an interesting methodological work that they did to kind of explore the value of these head impact sensors. So what do I think they're used for? I think if we can get an accurate sensor, I think they can serve as an extra pair of eyes. I have such tremendous respect for the athletic training profession and the task that they are asked to do of look at countless number of athletes, often multiple fields at one time, and understand who's at risk, who they need to look at. It is just an insurmountable task. So if the head impact sensor can serve as another pair of ATC eyes, I think that that would provide value. But what about sensors used in research? You heard me tell you about 20 minutes ago that I'm using sensors in research. So I do think they have value as long as you kind of understand the warts and understand their errors and think about how to incorporate that analytically. Maybe they might help us down the road guide diagnosis, but even as an engineer, I recognize that this is not a simple physics relationship. There are too many other variables at work here that determine whether an individual experiences a set of engineering loading and gets injured. Genetics, all those other variables that I spoke about, age, sex, whether they had a concussion before. So maybe they might be able to use speed-guide diagnosis, but I'm not too hopeful about that. I think they can be used to understand exposure, and I do think they can be used to guide innovations in protective design. So kind of going back to our lay press frenzy, I think we as a scientific community have a lot of questions to answer, which as researchers, you're always happy to hear that you know, we've got a career ahead of us and big questions to answer. And I think our approach at CHOP is really to understand how can we have kids participate in sports safely. Sports have so much positive impact on child health. So if I'm going to speak from a children's hospital perspective and think about the holistic health of kids, sports are good. Cardiovascular health, healthy weight, all of those other kind of soft benefits that come with sports participation. So I think our challenge as a scientific community is to figure out how to have kids participate in sports safely. Whether that's changes in rules, and I know Carolyn has led some of that work in Aubrey, whether that's changing protective equipment, whether that's changing surfaces that they play on, whether that's changing education. But I think we want kids participating in sports, we just want them doing that safely. So I will end a little over sharing some resources. Our website, which is chop.edu Concussion, we have a variety of different infographics that we have on our website that can be downloaded and made posters. We have some frequently asked questions videos about kind of questions that parents have about concussion. And if any of you want to come visit me in Philadelphia, we have an annual conference focused more on the clinical aspect of concussions that is held in April, and I'd love to see any of you there. And then last, I just want to acknowledge my large team. The ones in pink primarily focus on my auto safety stuff, and the ones in green are our large concussion research team. And so thank you for your time. It went a little longer than I thought. And please feel free to email me any questions, or if you have any questions now, I'd be happy to answer them. So thank you very much.
Always open for question. I'll start this. I'm interested in the mechanism of concussions. I'm glad that you're going to start a project using juvenile foresight model. I'm wondering why would you choose foresight model instead of some animal that is more closely related to human, for example, like monkeys. Why would you pick foresight?
So I think that's always a relevant question, is what animal model do you want to work with? So I'm going to answer that question in a variety of ways. We wanted to use a large animal model as opposed to a rat or mouse model because some of the behavioral and clinical metrics that we're using in humans, we felt we could replicate in pigs. We could study pig behavior. We're figuring out how to do eye tracking with pigs. And so that we wanted to do a large animal model. To get to your question of why not monkeys or chimpanzees, that work is really hard to do in the US. Particularly at Penn, who has a history in doing that work, and doing impact biomechanics on monkeys and chimpanzees doesn't usually get funded or accepted. Janet?
Thanks for a really nice presentation. I was interested in your vehicle entry work, and I think that I saw in the sled test where you were putting the people left and right and putting them, I think you called it the pre-collision.
Right, pre-crash maneuvers,
yeah,
right?
That the individual actually had their eyes covered. Is that correct?
No, they are just covered for presentation purposes.
Okay.
Because of our ethics rules, they can see.
Okay.
And we have in front of them kind of some colorful artistic things. We want them looking forward.
Okay.
We don't want them fixated on a point, but we don't want them kind of looking all over the place. So yes, their eyes are open. One thing I didn't mention is we don't give them a countdown, so they don't know when the event is starting. We kind of say, in the next 30 seconds, the event will start, because we're interested in as naive a response as we can get in a laboratory. I mean, obviously they know what they're doing, but we want them to kind of experience that startle reflex as well as we can do that in a laboratory.
So I guess that partially answers my question, but I was just wondering if you looked at actually the role of gaze in the response.
We have not. That's an interesting idea.
Okay. Do you have any ideas about what it might be? Because it also goes to the pre-planning in terms of muscle activation, if you know that you're going to be hit versus you don't know that you're going to be hit.
Yeah, and I would say that anecdotally, observing across the age ranges, I see that adults are able to kind of maintain that forward looking, and you know, intentionally or not, they're kind of focused on the same spot. Kids are kind of like all over the place. And whether that's kind of the maturity of their vestibular system of being able to do it, or they're just having fun, I don't really know. But I think that the idea of aware versus unaware is a relevant question to explore. The project that we're doing right now is kind of our first use of this device. You know, we've got a list of about 5 more research questions that we'd like to explore with it. You know, maybe rotate the that cage and that seat, so we're moving at an oblique angle, and study the effect of naive versus aware subjects, because it matters.
How much variability do you see within the sensor in the crash test dummy? Because that's your quote-unquote true value. If you keep doing the same thing over and over again without the helmet, how consistent is that response?
It's pretty consistent. So the design of the crash test dummy neck is specified by a calibration curve. And so all crash test dummy necks need to kind of meet this force deflection response. And so it's pretty repeatable within that range, given a given load. What was a little variable in that study, in part because of the external surface of the hockey helmet, is that even though we did our best as we could to align it exactly the same every time, if that impactor just kind of shifted a little bit on that hockey helmet because of the external contour, the response might be a little different. But what we compared is kind of a within test comparison of within a given test, what was truth and what did the sensor tell us, so that variability was actually okay within our analysis.
And was the wig always the same?
Yes, we squirted it 3 times when we were wetting it. So we did all the dry wig stuff first and then the wet wig. And actually that mattered, whether the hair was wet or not.
Change things.
Yeah, it did.
Can you go back to your thesis summary slide with the brochure?
Yeah. This one? Oh, really? Oh, I have to present. I see. Got it. I'm with you. This one?
Yeah, if you look at the bottom right slide, that's something that you would expect. If you look at the top right slide, it seems as if you would have 2 different sets of data. One set where it doesn't really matter,
Yes.
but whether you change the rotational input, and the other set where it does matter. Can you comment on that?
Yeah, I think it has to do with how these 2 different sensor systems measure or calculate rotational kinematics. So the G-force tracker has a gyroscope in there, so it's measuring rotational velocity directly. And so I think this is a more accurate representation of actually what the rotational kinematics are. With the HIT system, which is the upper graph, it is calculating rotational acceleration based on that array of 6 linear accelerometers. And so I think that there is error in that calculation based on the different parameters that we studied. So this is like a collapse of different directions, different speeds, different head-helmet interfaces. So that calculation to calculate this x-axis has greater error, has variability with those parameters.
But it seems that there are 2 set of data where systematically something has been done differently.
There hasn't. So like this set of data is just our higher speed impacts. And this is our lower speed impacts, if that's what you're talking about?
Yeah, but the one has a linear increase.
Here, and
the
this
other one doesn't have any increase.
Exactly.
Something is completely different in these 2 data sets.
I think it has to do with how the HIT system calculates rotation. Because the y-axis is measured directly.
Just a comment. I was looking at the data as well, and I was wondering if you actually have a system that saturates, that it might be a saturating effect because you have an enormous amount of difference in the acceleration, and you don't see a difference there. And my interpretation of that was that probably your sensor somehow saturated and you couldn't differentiate.
That is possible, and one of the challenges of working with the HIT system is that algorithm is proprietary, and it's a black box. You collect it directly, you send it to their server, they do something and send you back the answer. And so I did not get a lot of cooperation in understanding what that black box was, and issues like sensor saturation, what's the max value, I can't answer really clearly.
In this specific situation, though, I think it's the dummy's head that's saturated.
It shouldn't. The dummy, these impacts are much lower than what the dummy's designed to be loaded at. And I do know what that, the characteristics of that sensor are, because that was ours.
I have a question. I appreciate thanks for talk, by the way. I appreciated your position on what sensors are used for where, we really can't diagnose it, but we can use it kind of for the risk position. So you have these sensors. You talked about the linear sensors. You talked about the rotational sensors. There's others like finite element models and that type of thing. My question for you is, from a basic science point of view, what is your thought on what actually, from a mechanical or biomechanical point of view, what causes a concussion?
I believe that it is a combination loading environment. We see concussions. So people, I'm involved in some work with the NFL where we've reconstructed a bunch of on-field concussions using pretty detailed video data. One of the advantages of working with the NFL is there's lots of video. And so you see injuries where the loading is really purely linear, which I think is surprising to us. All the animal work really points to you kind of need rotation. And when I say linear, I mean there's global linear kinematics. So how that's translating down to brain tissue and what those axons are doing, I think they are both stretched and sheared such that their function is disrupted. And I think the role of finite element models to be able to answer that, if we know a global kinematic and we apply that, do we get those values of strain that we think, based on our kind of isolated animal preparations and isolated axon preparations, lead to dysfunction? Can we get that from global linear loading alone? I think is a question that we need to answer.
Yeah,
we got to use models.
That was the reason why I was asking that question. Of what do you think we know? What actually causes this?
I mean, there's been a lot of good work at the axon level to show if you stretch it X, you get these pathophysiological changes that influence function. And then they kind of stitching that story together to the athletic field, for example, and saying, okay, their global head kinematics is this. It's some combination of linear and angular in these various directions. How that translates to the tissue level, I think our finite element models are going to be needed to answer that.
That's what I was wondering, because I've seen people doing that. They have the brain in this fluid thing, and then you have an impact, and then the brain juggles back and forth and gets deformed and all. And yes, I've seen that in models, but is it not possible either in an animal or even with a low impact in humans to directly measure brain movement inside the skull? It seems to me that should be fairly straightforward, but I have not really seen people doing that.
So it's been done in cadavers with neutral density targets. So embedding neutral density kind of radiographic
Little markers.
and then loading the body globally in, dual plane X-ray or something like that, to be able to study that motion. That work's been done for adults. Probably the first one to do that is Warren Hardy at Virginia Tech. Focused really on the automotive environment, kind of translating that approach and that knowledge to the sports field hasn't really happened. One of the things that's really struck me as I've moved towards the sports biomechanics, the head injury biomechanics world, is the lack of communication between what we know from automotive safety to this other world. Those groups don't intersect very much, which is unfortunate, because I think some of that work has happened in automotive and not been translated to the sports world, and it hasn't necessarily been done in kids.
Because one of the things with these, accelerometers in helmets and so, I mean, they measure the acceleration very focally.
Correct.
And I always wonder, how does that relate to the brain acceleration? Because that's really what you presumably would like to know. So I could see that, because you mentioned maybe these markers are not accurate, or these sensors, but I would assume they are accurate, but they might not really represent very well what happens in the brain, depending on how you impact it and how, where exactly it's measured and so.
I think both issues exist. I'm not convinced they're all that accurate.
Oh, really?
And they are measuring some external kinematic. It's why I think the path to do helmet-based sensors isn't really fruitful, because we know that the helmet moves relative to the head, and that varies by hair, it varies by the inner lining of the helmet, and so putting that measure on that sensor on the helmet, I just don't think we'll ever have a really good understanding. For some of the work I'm doing from the NFL, we're pursuing the idea of development and implementation of a mouthguard based sensor. So at least that's kind of attached to the skeletal part of the body we're interested in measuring. Now you're still measuring it, remotely from what you want to measure, and so you have to worry about transformation and those things. But that's all math that you can figure out. I think the HIT system, which was really they were pioneers in this field, and they did really a tremendous advance in us understanding what the head might experience. But I think the technology that they used, the technology has kind of outpaced that. We have better ways of measuring these things now that I think will get us more accurate. But both of you are exactly right. We don't care what the head's doing, the skull's doing. We care what the brain's doing. And I wonder if this is part of what's at work when we see that subject 1 sustains maybe the same global kinematics. He's injured, and subject 2 sustains a very similar linear or angular acceleration, and they're not. It is their brain geometry, their brain anatomy, or just the slight change in direction of that loading dramatically influence what the two subjects' brains experience. So there's challenges ahead. What we can measure is global kinematics in a naturalistic setting on the athletic field, and so doing that additional work to relate global kinematics to the brain is another area that's really ripe for exploration.
All right, is there any other question for Kristy?
Yeah, the other thing that I was wondering, in your swerving experiments, what did you tell people to do?
Good question. So in the swerving experiments, you might have noticed there was a little footrest.
Yeah.
And so we asked them to kind of place their feet on the footrest to begin with, sit upright, sit normal, sit upright, normal, and place their hands on their knees. And then let what happened happen. And so you could see across subjects there were different neuromuscular strategies that they were employing, whether they thought that this was a whole lot of fun and we're just gonna ride the thing out, or whether they implemented strategies to try to maintain that upright position. Part of the reason we measured EMG, because we want to be able to sort out, just because we see different kinematics between one subject to another, does that mean it's because this subject really engaged their abdominal muscles and were able to kind of hold steady, whereas the other one kind of let themselves go?
It seemed to me exactly that's what it was. They kind of let it go, because I thought if I was in a car that was swerving like that, I would probably try to hold on to the seat or something, when somebody drives fast around curves,
Yeah,
hold
exactly.
on to that thing.
Right. We have there's a variety of different test conditions that we do, and so we do have one where we had a simulated armrest that they hold on to. The other thing that we've observed initially in our data reduction, so as I said, they do 4 cycles, and so four swerves is probably not realistic in a road. You're probably not going to swerve that much before you crash. But we see important differences between the first swerve, where they're somewhat naive. Then the second swerve, they always have the lowest excursion. Like, it's almost as if they're like, okay, I get it now, and now I'm going to have a strategy. And then they kind of swerve 3 and 4 and let go a little bit. So big excursion, little excursion, and then it kind of climbs back up. So I think they're implementing various strategies to try to kind of maintain vestibular balance.
All right, let's thanks Kristy again. Switch gear a bit. We'll jump into diabetes. A PhD student from Dr. Mark Angry's lab, Yang. He will talk about a micro-tissue engineering approach to generate human pancreatic islet organoids for the treatment of type 1 diabetes. See you next week.